Welcome friends on the subject of numerical methods under the subject of information technology in EPG Pathshala. Today we are going to take up the second chapter on ordinary differential equations. In our previous module, we learn about the basics of differential equation, what a differential equation is, what is meant by degree and order of a differential equation, what is an ordinary differential equation, what is a partial differential equation, and why do we need numerical methods to solve a ordinary differential equation in spite of having so many methods available in the literature. We began our journey with the first method in the single step series of methods, that is the Euler formula. Now, let us take recap of what we learned hurriedly in the previous module, and so we attacked the special first order initial value problem dy by dx equal to f x y x, where y at the point initial point x 0 is given as y 0, and we want the solution of y on the interval a to b. And this solution of the initial value problem, the method which is used is initial y is given at the point x 0 and the value of y, the interval a to b is divided into n equal sub intervals, and the length of each sub interval is h given by b minus a by n. And step by step we find the value of y, like y value of y at x 1 would be obtained from the value of y at x 0 and the function f x y information. Then the value of y at the point x 2, which we denote as y 2, would be obtained from y 0 and the function definition, and same way value of y 3 at the point x equal to x 3 will be estimated from y 2 and possibly y 1 and y 0, and this is how we go on. So, y at the point x n will denote by, for simplicity, at y n, y at the point x I will denote as y I, and similarly the derivative of y at the point x I. So, namely y dash at x I will denote by y dash I or y I dash. So, with this notation we begin, and we also learned that the Taylor series is the backbone of all these methods. So, today let us learn Taylor series in little more detail, and then we will go to the higher order cases of Taylor series, namely Runge Kutta family of formulas. So, let us begin with the Taylor series. Just recap the single step methods also, because all these methods which are learning are the single step methods. So, in the case of single step methods, they are direct methods, they are not iterative. All of them are based on the Taylor series. They use the estimated previous step and the function information, and we cannot determine the error in them. So, in the case of Taylor series, the advantage is that we can derive the answer up to any desired accuracy. The only difficulty is that we need to find higher order derivatives in this. So, what is the Taylor series? Let us review the Taylor series. See, the Taylor series y is a function of x. If we express Taylor series function y at the point x using Taylor series in the powers of x minus x I, what we get is y at the point x is y I plus x minus x I into derivative of y at the point x I plus second degree term x minus x I raised to 2 by 2 factorial, second derivative at the point x I. Now, third is x minus x I cube by 3 factorial, third derivative at the point x I, so on up to, if we want to keep up to nth power, x minus x I raised to n by n factorial, nth derivative at the point x I, and plus what remains is the remainder term, and that remainder term is n plus 1th power of x minus x I by n plus 1 factorial, n plus 1th derivative at some unknown point which we call as xi. We do not know what the point value is, but we know very certain that this xi will be in the range from x between x I and x. So, in this formula, see, y dash at the point x I will denote by y I dash, y double dash at the point x I for convenience will denote by y I double dash, and so on. So, y third derivative at the point x I will be y I 3, and a derivative of y at the point x I will be y I n, and n plus 1th derivative at the point xi I, we are writing it as it is. So, our Taylor series formula is given by y x is y I plus x minus x I into y I dash plus x minus x I square by 2 factorial y I double dash x minus x cube by 3 factorial y I 3, so on up to x minus x I raised to n by n factorial y I n plus x minus xi raised to n plus 1 n plus 1 factorial yn plus 1 at the point xi. Now, these yi are the derivatives at the point x equal to xi, and we can get in terms of derivatives of y at the point xi. If these values are available to us, then we can get the value of y at any point x. Obviously, x should be near the point xi in order to make these terms smaller. They are higher powers. So, if x minus xi is less than 1, these higher powers will go on increasing and will go on decreasing if this x minus xi is less than 1, and so we can ignore the higher degree terms. So, if we put x equal to xi plus 1, so y at the point xi plus 1 will be yi plus 1, and we get our term as yi plus 1 is given by yi plus h yi dash plus h square by 2 factorial yi double dash, so on nth power and remainder term. In case of Euler formula, if you remember, we had ignored second and higher degree terms, and we got the formula yi plus 1 is yi plus h yi dash, and that we call as Taylor series formula for n equal to 1. Now, today let us take the case n equal to 2 first, which gives us Taylor series method of order 2. So, in case of n equal to 2, we will retain up to h square by 2 terms, and that is our capital N will be 2, and the remainder term will be of order of h cube. So, our formula becomes, in case of n equal to 2, yi plus 1 is yi plus h yi dash plus h square by 2 factorial yi double dash, and plus the remainder term h cube by 3 factorial y third derivative at the point xi, because xi is not known. This term will ignore, and by yi plus 1 will be approximated by the expression as a sum of first 3 terms. So, yi plus h yi dash plus h square by 2 factorial yi double dash. So, we need to derive the values of, determine the values of yi dash and yi double dash. Y dash of course is available to us by the expression dy by dx is fx y dash, and so we can determine it. But higher order derivatives, like we need y double dash, so we will need to differentiate this equation to get y double dash. So, this is the dy by dx is fx by x. Differentiate this, we can use chain rule of differential calculus, and so y double dash x is derivative of f with respect to x plus derivative of f with respect to y, and into y is a function of x, so dy by dx. So, y at the point, we can substitute value of y double dash in our previous formula. In the previous slide which we had given, we can substitute here the value of y double dash, and what we get is y I plus 1, that is y at the point xi plus h, is approximately given by y at the point xi plus h yi dash is fx y yi plus h square by 2 y double dash is fx plus fy into f at the point xi yi, and third and higher degree terms we are ignoring. So, this formula is our Taylor series formula of order 2, which can be used to get the values. So, yi plus 1 is yi plus h yi dash plus h square by 2 factorial yi double dash plus order of h cube, which will be ignored. And this formula let us apply. Let us take this example, the same example we are taking which we had taken in our Euler formula discussion. So, our problem is dy by dx equal to x minus y at 0, that is 0 x 0 is equal to minus 2. I will illustrate the computational results by 3 step sizes, so that you can compare the results obtained with different values of h and realize that the smaller the h, better approximations we get. So, x 0 is 0, y 0 is minus 2, f x y is x minus y here. Taylor formula for order 2 already we have seen is yi plus 1 is yi plus h yi dash plus h square by 2 factorial yi double dash. Now, y dash is x minus y from here. Differentiate it rather than finding f x and f y, that also we can do. F x is 1, f y is minus 1 and so on, but directly we can differentiate this equation. So, we get y double dash is derivative of x is 1 minus derivative of y is y dash, and y dash we can substitute as x minus y. I get 1 minus in the bracket x minus y. So, 1 minus x plus y. So, substituting the value of y double dash at the point xi yi, y dash at the point xi yi. In this formula, Taylor series formula of order 2, we get yi plus 1 is yi plus h into yi dash is x minus y. So, xi minus yi plus h square by 2 into yi double dash is 1 minus xi plus yi. So, this is our approximation formula, Taylor series formula of order 2 for the particular example dy by dx is x minus y. We also know the exact solution of this differential equation is given by x minus e raised to x minus 1. So, step size h equal to 0.2 if we get, and we compute the, we begin with x, h is 0.2. So, x1 is 0.2, x2 is 0.4, x3 is 0.6, x4 is 0.8, x5 is 0.1. Exact solutions have been calculated from the expression x minus e raised to x minus 1. So, approximate solution using Taylor series of order 2 we get as for 0.2 minus 1.62, 0.4 minus 1.2724, 0.6 minus 0.951368 and so on. Finally, at 1 we get the value minus 0.370740, and you can compare these values approximate with the exact values that they are, these approximate solutions are much better than what we got from Euler formula. Later on, once we have learned, we will make the comparison of all the methods with different step sizes, we will do that later. So, the absolute error approximate minus exact absolute value of these is 1. You can very well see up to 2 decimal places they are all zeros, because now it is order of h square. We have taken the terms up to order of h square and error is of the order of h cube. So, h is 0.2, h square is 0.04, h cube is 0.008 and h cube 0.008 divided by 3 factorial, that is by 6. So, that becomes less than 0.001, and that is how the errors are coming out to be. At least up to 2 decimal places there is no error. And percentage relative error, that is absolute error by exact value of solution, these are the values of percentage relative error. Even at 1 the percentage relative error is less than 1. So, there is considerable improvement in the solutions obtained by taking Taylor series method of order 2 compared to Taylor series method for order 1, that is the Euler formula. Let us reduce the step size and see what happens. So, these are the results when h is 0.1. So, step size has become 0.1 and you can see that now up to 1, see the values 0.368541, 0.367879 and up to 3 decimal places we are getting zeros now instead of 2 decimal places, because h is 0.1. Now, h cube is 0.001 by 6, right. So, still further improvement, and the percentage relative error has boiled down to 0.179. So, 0.18%, it has considerably reduced here. There is one more point to be noted. See, one is the local truncation error, that is the order of our, in this case, h cube. But what happens is, like see, when we calculate x1, y at x1 using y at the point x0, the error is there, some error has come in, and as a result when we calculate y2 from y1, y1 already has some errors, and because y1 already has some errors, that error is carried forward in calculation of y2. Now, y2 will have the error because we got the error in y1 and the computational error result, truncation error. Now, when y2 has errors, now that y3 will have further errors, error of calculating in y3 and ignoring h cube terms, and also error due to whatever error in the values of y2 are. As a result, when we proceed slowly and slowly, the other errors also go on adding up. So, basically what we call as global truncation error, when we reach at x equal to 1 at the point x equal to b in general, right, what we have is the truncation error gets compounded also, and that is called global truncation error. So, global truncation error will not be of order of h cube, local truncation error is of the order of h cube, but global truncation error will turn out to be order of h square, it is 1 power h less than what the local truncation error is. Now, let us go further, let us take the result h equal to 0.05. So, I have shown you h equal to 0.05 further in this table. So, at x equal to 1, see now it is a relative percent error has come down to be 0.04, the value of absolute error at x equal to 1 0.000159, and in fact, it is 0.00150. This is all rounding up to 6 decimal places, they are almost same. So, that is how the Taylor series of order 2 has improved the results further. So, if I compare this Taylor series of order 2 with different step sizes, this is our x minus y, y0 is minus 2, this is the exact solution, this is the exact value given by. So, if we compare h equal to 0.2, h equal to 0.1, h equal to 0.05, we went on reducing the step size. Our approximate solution went on improving 0.37. These are the values which we obtained at x equal to 1. So, exact is 0.36788790. Using step size 0.2, we got minus 0.370740. At using step size 0.1, 0.368541, and 0.05, we got 0.368039, error of only 0.000159. So, reducing the step size improves the performance, that is what is expected and that is what is happening, and percentage relative error has come down from 0.77753881 to, in case of h equal to 0.1, 0.179826, and from 0.1 to 0.05, 0.043270. Let us take second illustration that we had taken in case of Euler formula hurriedly. Dy by dx is x upon y, y0 is 1, and again we will take the step size 1 and 0.5 and maybe 0.25 also. So, here x0 is 0, y0 is 1, function is x upon y. Taylor series formula, the one which we have is same, it is given by this expression. Y dash is x upon y. To get second derivative now, we will differentiate y dash. So, we will have to apply the rule. See, I am applying the multiplication rule, it is x into 1 upon y. So, derivative of x is 1, 1 upon y as it is, I will get 1 upon y minus now x as it is, and we will differentiate 1 upon y. So, x as it is, derivative of 1 upon y is minus 1 upon y square into dy by dx. So, dy by dx is x upon y. So, this is dy by dx, this is derivative minus 1 upon y square is derivative of 1 upon y, x as it is. I again repeat, this is, I am treating this as a product of x into 1 upon y. Derivative of x is 1, derivative and derivative of x is 1, 1 upon y as it is, plus x as it is, and derivative of 1 upon y is minus 1 upon y square into dy by dx. And so, this term becomes y square minus x square upon y cube. So, the formula is yi plus 1 is yi plus h x I upon yi, h square by 2 yi cube minus x a cube upon yi cube, and exact solution we know is given by y equal to root x square plus 1. So, if we take h equal to 0.5 and we go from 0 to 5 here. So, we have 10 steps to be done, and so the exact solution at x equal to 5 is 5.099 and approximate we get is 5.113 using step size as 0.5. Absolute error is 0.013993 and percent relative error is 0.274433. If you reduce the step size to 0.25, see if you compare, now the percentage relative error has become 0.062658. Absolute error has come down to 0.003195, an improvement, and further 0.125 to make the table look small and be legible. I am not showing the in between steps, but all in between steps are there, 0.125, then 0.25, then 0.375, then 0.675 and so on. So, these steps are not being shown, and finally, at the interval of 4 now I have shown you the steps. So, at 5, see now 5.0099, 5.099. So, up to 3 decimal places we are getting zeros, 0.000766, because the h is still very small. So, as because h cube power becomes smaller, so truncation error goes on becoming smaller, and the percentage relative has come down to 0.015%. And so, again if we compare at final value at x equal to 1, the values in the table form, see the exact is 5.099020, at with using step size error was 0.013993, using step size 0.25, error is 0.003195, and using further smaller step size 0.125, error is 0.000766. So, this is how the reduction of the step size improves the performance of the method. Now, let us see, similarly we can have a Taylor series method of order 3 also, but most commonly method employed are Taylor series of method of order 2 and order 4. So, just let us take the case of Taylor series method of order 4. So, in case of Taylor series method of order 4, our capital N will be 4, will keep the terms up to 4th degree, 4th power of h, and will ignore the 5th and higher degree terms. So, our formula is yi plus 1 is yi plus h yi dash plus h square by 2 factorial yi double dash plus h cube by 3 factorial third derivative, so on, and h raised to 4 by 4 factorial fourth derivative. And this is our 5th term is our remainder term, which we will ignore. This will denote the truncation error. But now see, here we will need to evaluate, differentiate the equation thrice. Dy by dx is f x y, y dash is available, but we need to differentiate to get second derivative, then again differentiate to get the third derivative, again differentiate to get the fourth derivative. So, in case the function is not simple, the derivatives become complex. Again let us repeat the same illustrations. So, dy by dx is equal to x minus y, f x y is x minus y. Our Taylor formula is now yi plus 1 is yi plus h yi dash plus h square by 2 factorial yi double dash, h cube by 3 factorial yi 3 plus h raised to 4 by 4 factorial yi raised to 4, this fourth derivative of y. Y dash is x minus y, y double dash is 1 minus y dash, so 1 minus x plus y. To get third derivative, differentiate this equation. So, y third derivative differentiate y double dash is equal to this equation. So, this is y third derivatives differentiate 1 minus x plus y. So, minus 1 plus y dash. So, y dash minus 1, and substitute the value of y dash as x minus y, we get x minus y minus 1. And to get fourth derivative, again differentiate this. So, y 4 is differentiate x minus y minus 1, or it is equal to differentiate y dash minus 1. So, you get y double dash and substitute y double dash as 1 minus x plus y, you get 1 plus y minus x. So, this x minus y equation is very simple. We got derivatives, third derivative, fourth derivative very easily, and so we can substitute now these values of derivatives in our approximation Taylor series formula. So, yi plus 1 is given by yi plus h yi dash is x minus yi plus h square by 2 1 minus xi plus yi plus h cube by 3 factorial xi minus yi minus 1, and h raised to 4 by 4 factorial into fourth derivative, that is 1 minus xi plus yi. So, now we have this expression, and this expression is used in the computations to get estimate yi plus 1 from the value of y at the point xi. So, let us again look at the results hurriedly. Here h is 0.2, n is 5. So, we get it. Now, you can have a look, see because we have kept the terms up to h raised to 4, right. So, here you can look and you go up to 1. See, error is, this is basically we have for display purpose we have retained only 6 decimal places, otherwise for all practical reasons you are getting exact values up to 6 decimal places, minus 0.367885 minus 0.367879, error is 0.000006. So, percentage relative error is 0.001576. If you further reduce h equal to 0.5, say it is almost, you are getting up to 6 decimal places, almost the same answer. This is only rounding, it is 79 it has become. So, here it is basically exact result you are getting almost here, all absolute errors are zeros only here. They are exact results you are getting up to x equal to 1 with h equal to 0.1 if we are using Taylor series method of order 4 in this particular example, and further 0.05 definitely you will get the exact answer. So, if we compare this Taylor series formula for order 4 for different step sizes, 0.2 error is 0.000006, 0.1 it is no error, absolute error, 0.05 actually no absolute error, This is all more digits are retained, and that is why you are getting these figures. For display purpose, we have only displaying 6 decimal places. So, up to 6 decimal places there is no error, and these figures you are getting because we are using more digits in the calculation. Otherwise, if we use these only 6 figures, the percentage error will also come out to be 0. With this now, once we have learned Taylor series formulas, we come to Runge Kutta formulas. See, Taylor series formula is the backbone of these methods. See, disadvantage of Taylor series method in its raw form is, as you realize, like in the case of dy by dx was x by y, I did not illustrate to the method of order 4. For the simple reason, second derivative itself has a long expression, and if I go to write down the third derivative, fourth derivative, then employ, the derivative expressions go on becoming complex. And moreover, whenever you want to solve a particular differential equation, you need to first derive derivatives and you have to hard code them in the program, and so this involves lot of computational work, lot of labor before implementing on the computer. So, question is, can we have a better way, better mechanism? And Runge Kutta formulas are the same because they are based on the Taylor series formulas also. We will see how they are done, and to remove this advantage of Taylor series formula, what we have is Runge Kutta family of formulas. And so, just let us take one by one these Taylor series Runge Kutta formulas. See, the first thing is they are single step methods, they are families. So, the way we have Taylor series, we have Runge Kutta formula of order 2, Runge Kutta formula of order 3, Runge Kutta formula of order 4. Corresponding to Taylor series of every order, we have Runge Kutta family of Runge Kutta formula. So, Taylor series of order 2 corresponds to Runge Kutta formula of order 2. Taylor series of order 1 corresponds to order formula, Runge Kutta formula of order 1. Taylor series of order 3 corresponds to Runge Kutta formula of order 3. Taylor series of order 4 corresponds to Runge Kutta formula order of 4. So, what we have is family of these Runge Kutta formulas, and they were derived by the persons Runge and Kutta. And so, they emulate Taylor series, and the advantage of this formula is that we do not need to differentiate. So, again let us consider the same initial value problem, dy by dx is f x y, y x 0 is y 0 on the interval a b, and our the same objective we have to find the function y x which satisfies this equation, dy by dx is f x, y x 0 is y 0. So, let us again say begin with Runge Kutta method of order 2, and then we will take the Runge Kutta method of order 4. So, Runge Kutta method of order 2 is equivalent to Taylor series method of order 2, and this formula is derived as the Taylor series method is. It is derived by using terms up to second power of h and ignoring higher order terms, and so local error is of the order of h cube as you have in the Taylor series. The advantage is that there is no differentiation procedure. So, directly they can be implemented, all you need to is input in the program the expression for f x y, that is all, and the same program can be implemented. And so, there is no differentiation procedure involved here, and it just needs in the method in the formula 2 evaluations of function f per step. So, it is very convenient, very handy to apply, and gives the same accuracy as Taylor series method of order 2. So, before we proceed, let us solve one example and let us understand the formula. So, Taylor series formula is given by, see, dy by dx is f x y y x, y I plus 1 is given by y I plus half k 0 plus k 1. And what are k 0 and k 1? K 0 is h f x I y I, and k 1 is h f x I plus h y I plus k 0. So, this is the Runge Kutta formula of second order. Y at the next step, that is y I plus 1, is y at the current step y I plus half. We need to compute two constants k 0 and k 1. K 0 corresponds to the term of degree 1. See, that is the same you have in Euler formula h f x I y I, that is over Taylor series h y I dash, y I plus half h y I dash, that is what it corresponds. And k 1 is h f at the argument x I plus h, that is x I plus 1, and y I plus at the argument what K0 you got. So, this is Runge Kutta method of order 2, and this we will use to solve the same example dy by dx equal to x minus y, y0 equal to minus 2. Let us do one computation manually, so that you get the feel of this method. So, here see in this y1 is y0 plus half. So, y0 is minus 2. So, minus 2 plus half into k0 plus k1. Now, what is k0? K0 is h f x0 y0. So, h is 0.2, we are using the step size 0.2 first. So, h is 0.2, f x y is x minus y. So, f at the point x0 y0 is x0 minus y0. So, this gives 0.2 into x0 is 0, y0 is minus 2. So, 0 minus minus 2. So, 0.2 into 2, and that is 0.4. K1 is h into f x0 plus h. So, x0 plus h, x0 is 0, h is 0.2. So, 0.2 into f at 0.2, y0 is minus 2, k0 we have computed, substitute the value, minus 2 plus 0.4. So, it is 0.2 into f at 0.2 minus 1.6. So, 0.2 into 0.2 plus 1.6. So, 0.2 into 1.8, and that gives the value 0.36. So, substitute here. So, y1 is minus 2 plus half into k0 plus k1 is minus 2 into 0.5 into 0.40 plus 0.36. So, minus 2 plus 0.5 into 0.76. So, minus 2 plus 0.38. So, answer is minus 1.62. If you remember, it was the same as we got using Taylor series of order 2. Now, before we go to computational results, let us learn how we derive, let us conceptualize how we derive this method of order 2. See, what is done is you try to derive the formula of the type yi plus 1 is yi plus a k0 plus b k1. A is unknown, b is unknown. K0 is fixed h f x I yi, and k1 is h into f x I plus alpha h, alpha is a parameter to be determined, yi plus beta k0, beta is to be determined. So, there are 4 unknowns a, b, alpha and beta. We know by Taylor series, see the derivation is based on Taylor series only. So, yi plus 1 we know the Taylor series, if we are returning up to powers of up to the terms up to power of h equal to 2, we get yi plus h yi dash plus h square by 2 yi double dash, that is yi plus h yi dash plus h square by 2 f x plus f y into f, that we have done previously just now in at the point x I y I. So, this is the left side in this equation. K0 is h f x I y fine. For K1, which is given by h into f x I plus alpha h y I plus beta K0, Taylor series of 2 variables is used to expand it, and it is expanded in powers of h, and then from both the sides, the left side is yi plus 1 equal to yi plus h yi dash plus h square by 2 yi double dash, and right side also has powers of h, which is obtained by expanding Taylor series of order 2 again, and a higher degree term being ignored, but of 2 variables. And then the coefficients of h square are equated on both the sides. So, you get equations, coefficients of h square are equated, and then those equations are solved for the 4 unknowns a, b, alpha and beta. In this case, the number of equations obtained are 3 and the number of unknowns are 4. So, you have a freedom of choosing at least one parameter independently. So, there is more than one solution to Runge Kutta method of order 2, there is more than one choice of solution. So, the most common solution which we do is the a, that is our alpha equal to 1 and beta equal to 1, and here we write down. So, and a and b equal to half, that is the most convenient solution we do. So, in this Runge Kutta method of order 2, we get 3 equations, 4 unknowns to be solved for, and so we are free to choose one of them, and as a result there can be more than, and there are more than one formula which are used in practice, and for the convenience the simplest to take the values are your coefficients a and b equal to half, and alpha is equal to 1 and beta is equal to 1 by 2, and which is the most common Runge Kutta formula of order 2. There is one other also where alpha is taken to be as 2 by 3 and beta is to be taken as 1 by 3. Now, the way I showed you the method of deriving Runge Kutta formula of order 2, in exactly similar way Runge Kutta formula of order 4 is derived. It is further more complex because we have K0, K1, K2 and K3. There are 4 terms to be determined. Powers of h raised to 4 are retained and power of h raised to 5 and onwards are ignored in that. But the concept, the method is same, that left side is Taylor series yi plus 1 is yi plus h yi dash so on up to h raised to 4 by 4 factorial 4 derivative at y, and the right side is the Taylor series of you get the terms in 2 variables which is expanded in the powers of h, and the powers of h equal powers of h coefficients are equated, but this time the number of unknowns are high and number of equations to be solved are high. So, those who are interested in going through the proof, they can refer the other books which are already mentioned to you in the references. So, there are many books which contain the proof. You can also try to derive on your own the proof of Taylor series of order 4, and definitely. So, the advantage of this Runge Kutta method of order 4, order 2, all this Runge Kutta family, and in general see we can have Runge Kutta formula of order 3 which are not touching, and we can derive Runge Kutta formula of any order, say order 5, order 6, these formulas using the same concept, and they give the same order of accuracy as Taylor series of order n. So, we would be in our next module, we would be taking up examples of Runge Kutta family of order 4, we will solve them, and we would also like to take a comparative study of the results obtained by Euler method, Runge Kutta method of order 2, Runge Kutta method of order 4 as well as Taylor series method. And then we would like to move to multi-step methods, because what we have learned so far are single step methods, and in multi-step methods as we know it, the method is when we try to find y at the point x I plus 1, y I plus 1 will be obtained not only from the value of at one previous step y I, but it will also use the values of y at more than the one previous step y I minus 1, y I minus 2 and so on. And in these multi-step methods, we would like to focus specially on what are called predictor corrector methods. In the case of predictor corrector methods, we have two formulas, one is the predictor formula and other is the corrector formula. Predictor formula, as the name is, predicts the value, and the corrector formula is the iterative in nature. You go on applying it, as the name is, goes on correcting the values till we get the constant results. There are two, there are many predictor corrector formulas. We would like to focus on two of them, which is Milne-Simpson and the other is Adams-Boschford. So, thank you for coming and visiting EPG Pathshala, and once again thank you so much, and we meet again to discuss further on Runge Kutta family of order 4 and these predictor corrector formulas in the chapter of ordinary differential equations to be solved by numerical method. Thank you.